The energy that birds use during flight is mostly spent on carrying their mass and dealing with the drag of air against their body. These energy costs are particularly important for long-distance migrating birds that put on large amounts of body energy stores prior to their migration and need to arrive at their breeding or wintering grounds at an appropriate time. For example, when great snipe fly from Sweden to equatorial Africa each autumn, they do so non-stop for 68 hours, covering 6,000 kilometers and traveling at an average speed of 24 meters per second. Such migratory behavior creates a paradox of avian flight. This is because increased body mass is presumed to increase the energy costs of being airborne. But as yet, there have been no satisfactory studies that have measured these costs in the field. We undertook a novel design of experiment that involved loading weight onto free-flying homing pigeons. We also attached to them a slimline data logger to record their heart rate. The study was undertaken in northwest Wales near the Menai Strait. The pigeons were released in a flock 10 kilometres from their loft. The birds were flown twice over 2 consecutive days in a within-subjects design. Half of the flock had no extra load, the controls, and the other half a thin lead chest plate of 5% of their body mass. 5 days later, this design was repeated, but with 10% added mass. The sensitivity of the heart rate response to the increased weight is clearly visible from early in the pigeons' flights. The coloured lines represent flights carrying a 10% payload, and the black and grey lines control flights. The added loads caused only a small increase in mean heart rate compared to the control flights, which indicates that flight costs increased by only 3.7% when the birds were carrying a 5% payload and 6.7% when they were carrying a 10% payload. Aerodynamic theory predicts that the minimum mechanical power for a bird to fly as it gets heavier scales with a body mass exponent of 1.17. As a result, transporting mass through the air should be less economical for heavier individuals. Yet our data suggests this exponent is far less, and indeed the relationship is hypoallometric, with an exponent of around 0.75. Pigeons can carry extra mass very economically during homing flights. Can these hypoallometric relationships be reconciled with aerodynamic theory? Aerodynamic theory to date has assumed birds fly at the speed that minimizes their power requirements. However, the pigeons in our experiments flew much faster than this. At such high speeds, the effect of the added mass becomes diluted relative to the effect of the rapidly increasing parasite drag, which is proportional to speed squared, and associated additional power, which is proportional to speed cubed. Thus, at higher speeds, the increase in mass results in a proportionally small additional energy cost, as the power speed curves for the different payloads do not run parallel but converge. Generalizing to avian migrants, we propose that flying fast helps such species not only reduce their journey times, but also increase their flight ranges, because at such speeds they can carry additional fat and muscle for a relatively low aerodynamic penalty. If you'd like to find out more about this research, you can access our paper published in Scientific Reports at the journal's website, or contact the corresponding author, Dr. Charles Bishop.